So this is really a hands-on workshop. I plan to talk a little bit about the problem and go through some of my code and kind of tell you how this data set is structured. But then the idea would be for you to train some machine learning models on the spot, and I can go along here and help you. And the main goal is for you to take part in a competition set by a university in Spain, where they evaluate these models on a blind data set. So if you have R and RStudio installed, you can open them, because that's the intention. Okay. Yeah, the first part of the workshop is talking about the data set. It's called UJIIndoorLoc dataset. UJI stands for Universitat Jaume I in Spain, and it is so far the biggest data set available for indoor positioning. That means getting the position of people using their smartphones based on the signal that those smartphones receive from the routers, the wireless access points around you. By the way, this signal that you receive from the routers is something that you can check if you have a MacBook or any Apple device, and you click Alt and then you click on your Wi-Fi. You will see here that right now I'm connected to this network, and the received signal strength intensity is this one, minus 46 right now. You can also download some applications such as NetSpot, and here you can check all of the access points around you, and this the column that says signal would be the strength of the signal that you are receiving from each one of these wireless access points. So this is data that it's most of the time hidden, but that all the devices connected to the internet are getting constantly. And even though you don't know where those routers are positioned, the signal strength can be a proxy for the distance where you have all these access points around you. And because you have in some buildings, like here today, or in a university, you have many of them around you, they can really help positioning someone in an environment where GPS would not work. So that's what we're going to use. In this particular data set, they used 520 routers, and they had some people running around the university with 24 different smartphones, Android smartphones, all of them. And they previously mapped the university, so they knew the real exact coordinates in many points of the university. So someone would be walking around the university, and when they would find one of these spots marked where the coordinates are known, they would record the received signal strength intensity at that particular spot. This is the university in Valencia, Spain, where they recorded it. So it's 3 different buildings and each building has 4 or 5 floors. It's quite a big space. And what we will be interested in knowing is the longitude, the latitude, and then the altitude will be measured in the floor. Okay, so we will have access to 3 data sets called training, validation, and testing. The first one, the one that we will be using to train the models, has 19K observations and was recorded like 4 months previously before the other 2. And we can test our results in the validation set. We don't need to split the data ourselves. And then the testing data set is not labeled. Only the researchers that created the dataset have the labels. So the idea is that you make some predictions on the testing set, and then you send them this floor, latitude, and longitude to them, and then they get back to you with, okay, you are that far off. So you can consider participating into the challenge. Okay. This is a challenge that we use in our Code Academy. I skipped my introduction. I'm a mentor in a Code Academy in Berlin. It's called Ubiqum Code Academy. And in our program, which is like 5 months to teach people how to be a data analyst, we use this data set in a project to teach machine learning to people using R, because it's pretty good. It has 3 target variables when usually you will only have 1, and one of them, like the floor, or you can also predict the building, but it's very easy, are categorical, so you do classification, and then the coordinates are regression problems. And the understanding how this signal works is, and understanding how the dataset was recorded and really exploring the dataset is going to be a major part of achieving good accuracy, good results. But there's also a lot of room for tuning the models. So between that and that it's a dataset where you have a few hundred features, you can use your machine, but still you cannot just run any model with the full data set and expect it to run in seconds. There are some challenges if you want to iterate quickly through different preprocessing and through different models. And then there's this blind competition, which makes it a bit funnier. We do it in 3 weeks, this project, because we throw the information and the data set to the students without many more things, and it's for beginners it's really a complex problem, but for people who come here to this congress, I guess that in 90 minutes we can get it done. We will use the Caret package. How many of you have used the Caret package? Okay, so like 10%. Okay. The Caret package is one of these meta libraries for machine learning. In R, all the packages for training machine learning models were developed independently. And if you wanted to run many different models and tune them, say 10 years ago, you would have to understand how each one of these packages work to then be able to tune the models and even run them, etc. So this guy, Max Kuhn, created a package that makes it super easy to iterate through many different models. And there is of course, the concern that if you understand a problem, you can know beforehand that one model is better suited than others to solve it. But before knowing the problem, each model is equally strong or equally a good candidate to solve it. And that's the no-free lunch theorem that Max Kuhn based the caret package on it. What we're going to do is we're going to run a loop through different models, different methods. And then each one of these methods goes into the train function of the caret package, and the train function at the same time runs a loop. It basically does cross-validation, which consists in dividing the set in different parts, training the model into as many parts minus one, and evaluating the model into the remaining part, and so on, doing that, leaving out one part at a time, and then averaging the performance of your model through all the folds, all the parts that you left out, and then just doing the same for many different parameter sets, many different parameters for each algorithm. And caret does that automatically, which makes it incredibly easy to run a few models in a few lines of code. Okay, so for the ones who want to follow the coding challenge, you can already start installing the caret package because it takes some time. And this way, you will be able to have it installed when we start modeling. Even if you set dependencies to true, it is very possible that some libraries that are required for running package do not get installed, and then when you load the package, it triggers a warning or an error saying, hey, you still have to install this other library, and you have to do that a few times. It's a bit annoying. But in a few minutes, you can get it installed. Then the package has more than 200 models available, but because of time constraints, we are going to only iterate through these 4 models. Ranger is an implementation of random forest that is it's very well optimized. It's very time efficient. Then we're going to use another tree-based model, gradient boosted trees, or gradient boosted machine. And then the k-nearest neighbors, and a support vector machine with a linear kernel. Everything that I will use, it's in this GitHub repo. If you go there, you can clone it. In case you have never cloned a GitHub repo from R, RStudio has a very nice interface to do so. You can just go to the link of the GitHub repository, and you click on clone and download. You copy the HTTPS link, and then on RStudio you open a new project, and then you go to version control, Git, and you paste there the link. And this way, everything that I have in my GitHub repo gets copied into your RStudio project, which is very convenient.
Can you flash the link? Thanks.
Yep. I noticed that I'm going a bit quick, so if you have any questions right now, or if you have any comment or any difficulty following, let me know, okay?
Sorry, just trying to do that now in version control.
Okay. Okay. Then what I'm going to do is that I'm going to stop in a bit. Let me check. Yeah, I'm going to pause for 5 minutes and go along the room, helping people to set up the thing. And then I'm going to go through the initial exploration of the dataset through my notebook. And then we can start running the models, okay? Let me know if you want me to help you set up the thing.
Do I just need to install something else? In version control?
Yeah, and then you go git.
Do I just need to install?
Ah, yes.
Is it like a separate package or do I install?
Ah, no. Okay.
Sorry, it's probably
No, yeah. Yeah, I forgot that you have to install Git, yeah.
I just read like random forest and think.
Yeah, okay. Yeah. You will need to go to install Git for Windows.
I'll see if I just do that.
Okay, forgot to add that if you don't have Git installed, you will need to do so. So if that's the case for you, it might be easier if you want to follow, for you to just go to the scripts folder and download each one of the R scripts, or just copy paste the code into a new script in RStudio. You can download the zip archive. Okay. Okay, that's a good solution. Yeah, you can download here on clone of or download. You download the zip. It will take some time. And then you have all the files in your computer, so you can just go to this folder and open the files. Yeah, I don't think so. Yeah.
I mean, I guess either way, doing by zip, because what I tried to do earlier is of the new project, and then more Python, so I'm less familiar with R, version control, and then you paste the Git repository around here, and then it's the same speed, I suppose. It won't be faster this way, but it'll be exactly the same. You reckon it might be a bit faster this way?
I think it should be faster this way, yeah.
Just
but maybe you don't have Git installed. Do you know if you have Git installed in your computer?
Well, I have Git desktop, yeah.
Okay.
Carrot is already installed as well.
Okay, cool.
So it's just this one.
Okay, nice. Anyone here with some help?
fix that.
Okay, yeah, it's unloading.
It might be that everybody is scrolling at the same time.
It's probable. Yeah, it's also quite a big repository, but yeah. Okay, some of you are cloning the repository, and that will take some minutes, so I will start showing the first notebook, which is the exploration of the dataset, and also some preprocessing. And the problem is that I don't see how well you see this screen. It's a bit dark. It's a bit, okay. Let's try to change again to the light scene. This one better, no? Okay, cool. Okay, for this one, we only need the tidyverse and plotly libraries. And we will be exploring the two datasets that we have labeled, the training and the validation datasets. We use the functions from dplyr to read. Just with the default settings, they do the job. And then we see that we have 529 features in the datasets, and at the end, the last 9 features are the ones that matter. Longitude, latitude, floor, building, space ID, relative position, user ID, phone ID, timestamp, etc. for both datasets. If we were to explore the first features, what we would find would be just WAPs. Here in the first 520 features, we have the list of all the access points, all the routers, with the signal strength. So what we will do is first to give some names to the dataset for it to be more easy to code with it, easy to interpret as well. Then all the features such as floor, building, space ID, relative position, the user, and the phone IDs, we will convert them to factors because they are categorical features, even though they have a numerical code. We will do that with apply. So we are applying the asFactor function to all the columns that we have selected. I don't know the level of R programming that you have here. Are you familiar with this kind of pipes part of the dplyr? Yeah, okay, good. So what we are doing here is that we are selecting all the categorical features, we are converting them to factors, and then we are merging them with the rest of the of the features that we are not touching, and then we convert the time feature to POSIX-CT for it to be a timestamp, and we do that for both the training and the validation dataset. Maybe I should do it even bigger. Now, we have 19,000 observations in the training dataset, and they have a lot of detail. If you look at the longitude and latitude coordinates, you see that they have a lot of decimal points. But if we then check at the unique values for longitude, latitude, and floor, and we count them, we see that, in fact, we only have 933 different spots where the RSSI was recorded for the training set, and a bit more than 1,000 for the validation set. So this is part of the nature of how this data set was recorded, and how any data set for this kind of problem will be recorded. The only way to label the data is for you to really go and map somehow the buildings that you are researching, and it's quite difficult and quite time-consuming to do so. So these guys mapped 1,000 different points where they knew the coordinates from them, and they told people to just run from one of these points to the other, and then recording the RSSI for these spots.
Sorry, you said 1,000, not 1,000.
We have like 900 for the training set, and 1,000 for the validation set.
But in total is 2,000. Was the same points?
It's something that we can investigate later. It's very likely that they are different. So they're going to be 200 in total, yeah, because the data sets were collected with 4 months of different one between the other. We can plot these points, and we will use Plotly for that. So we have an interactive visualization. Okay, so this is the latitude, longitude, and the floor plotted. And we can clearly see, if you remember the picture that I showed with the buildings of the university, they had this shape. So all the 3 buildings with the 4 or 5 floors were pretty much covered by the dots. You can see all of these are the unique spots where RSSI was recorded. And now we can check what you were commenting. We can merge both data sets, identifying them first in a column, to see if the spots in the training set and the spots in the validation set are the same, or if they are different. And we have them here. You see how they are not exactly the same points. So you were right. And for some parts of the building, like this part here, we only have records for the validation set. So that's something to consider when you are training the model, because you're training it for the test set, the last one of the sets, where you don't know exactly where are the points there. Okay, let's move on. Remove these columns that we created, and now we will just start with some cleaning. We check how many unique observations we have, and we find that we have a few duplicate rows. We don't want them, so we keep only unique observations.
What does it mean? Is that this one measurement point, so the location, or is it that really the measurement is being predicted? So that two different devices or two different days measure the same location? Or
You mean the duplicates? Yeah, they're not normal because it means that both latitude and longitude are exactly the same. That's not that difficult because we have 20,000 observations but only 900 different unique spots. But also the timestamp is the same, and that is a bit more strange. And all the measurements for the 500 routers are exactly the same as well. So it's something that we have to pay attention at that. Now, when we look at the distribution of all the values from the routers, the signal intensity values, we will start to get an idea of why can we have duplicates in the first place. Let's select only the wireless access points and just merge them and plot the distribution for absolutely all of them. And this is a distribution, so the values are between minus 100 and 0, more or less, or no, minus 30. That's for the validation set. For the training set, they are between minus 100 and 0 here, yes. So we have a slight difference in the range of values that both datasets cover. And here, to plot these distributions, I filtered out the values 100. If I don't do that, this is what we get. We have a huge peak at 100, at exactly 100. And this is because 100 was the value set to no signal at all. And it's not the best choice to keep it like that if we consider that the strongest signal possible would be 0 and the weakest signal possible would be more or less I think it's minus 104. So having the values where we do not detect any router at all at positive 100 is definitely not ideal. And what we do is we pick an arbitrary number. In this case, I picked minus 110, and I assign the values without any signal whatsoever to this one. So it's like saying, if I detect the weakest possible signal, my device will say -104. But if I don't detect anything at all, even less than that, -110. This is part of the pre-process, like everything that I'm doing, where there is not one single good option. I'm just showing one possible pre-processing that I chose to do, but you can do a different one, and you will have to do a different one because I didn't win the competition. So if you want to win it, you will have to refactor that. Then, if you remember, when we were comparing the distributions here between the training set and the validation set, we saw that in the training set we had some values that reached even 0. So very, very strong signals compared to the validation set, where the strongest possible value is -34. Let's load the plots. Once I finish with this expression, I will go back to help the people that probably right now you have already downloaded the repository. Has it already downloaded the repository? Yeah, okay, cool. This is without the filter. No, this is because I was filtering 100s, but I already converted the 100s to -110. Yeah, this is validation, and this is training. There is this small group of outliers here, and we want to know what happened there. We can also check here how the maximum value for the training set is 0, whereas the maximum value for the validation set is -34. We can try to visualize all values in the training set that are not these undetected signals. To do that, I use gather, which is the dplyr function to convert a wide dataset into a long dataset. I can show what this does if you want. It might be interesting if you have never done this type of transformation. Like, a wide dataset is what we have, and it's basically every column is a feature. Takes some time. Every column is a feature, and then here we have the values. But if we convert it from wide to long using gather, then we have only one column with the name of the feature, and then another column with the value, the key and the value. Usually in R people used melt, but now that everyone uses the tidyverse as much as possible, gather is the way to go. So yeah, we filter out the signals that we don't receive, and then we plot it in a scatter plot. Okay, so this, maybe it's better this way. this is our data set. This is all the wireless access points in the x-axis and the RSSI values in the y-axis. And I remember that I have filtered out the minus 110, which is the values where we do not receive any signal whatsoever. And you see how there are these guys here in between minus 25 and 0 that are anomalies, very strong signals. And then we have WAPs without any detected signal, and we have to assume that it's because in those WAPs all the values are in the minus 110 that we excluded. So what we will do is that we will check the maximum strength of RSSI of each one of the WAPs. We have it here for both training and validation. See, some WAPs have a maximum strength of minus 93, minus 86, and some of them, like these two guys, they have minus 110 as the maximum value. That means that for some WAPs, never was recorded any signal at all. And the same for validation. This WAP has never received any signal. And we can even check that they are different. They are different WAPs, the ones that are not receiving signal. We can visualize that here. So we have for the training set, we have like no, this is the validation set. For the training set, we have around 50 WAPs where the maximum signal received is minus 110. That means WAPs that are not detecting anything at all. And then we have this group of, let's say, normal measurements, and then this small group of very strong maximum signals. Whereas for the validation, we have a much bigger group of WAPs that are not detecting anything, but we do not have this group of outliers that detect very strong signals. And what we do at first is we filter out the WAPs that are not detecting anything in both training and validation. We check that there is no overlap in these WAPs that are not detecting anything, and that has to do with the fact that the datasets were recorded with 4 months of difference between each other. And probably there were some WAPs, some routers that were changed, that were working when the training set was recorded, but were replaced for other WAPs when the validation set was recorded. So what we will do is we will exclude all the others. What happened here? Okay, probably I am executing the code on objects that I already modified, and it's giving me some errors. But mostly what I do here is that I delete all the WAPs that do not receive any signal. And then from the training set, I delete all the WAPs that receive, I check for all the WAPs that receive these very strong signals. And I find that all these very strong signals are detected by up to 81 different WAPs. So that's a very, very high number for just deleting them because they are receiving unusually strong signals. And instead, what I do is that I check for which rows are detecting these very unusual signals. And it turns out that it's only like 500 rows that are detecting these signals that correspond to some phones that probably were not running very well. And we exclude these phones. And that's more or less all for preprocessing. I will now come back to the guys that were trying to run the code, and later I will come with the modeling. Okay. So who's trying to run it, or who wants to try to run it?
I wasn't on.
No? Okay. Okay, then I will just, yep. I will switch to the modeling phase, and I will show you how the models are run.
By the way, in the end, like with your run, I saw that you have like lots of files, so you would run them in sequence rather than you didn't have one to test all of them.
Yeah. This kind of errors, like the one that happened to me, I find that they happen a lot when you are using notebooks, because they are good for showing plots embedded in the code and everything, but when it comes to being consistent, I use normal scripts, and those are the ones that I run. I have some scripts labeled with 1.1 and 1.2. You can run either of those. The 1.1 has exploratory data analysis in it, and the other only has the code that runs that applies some transformations into the data. So I'll run that. And
remind me the goal. What was there? What are we trying to focus?
So here we are just preprocessing the data, and at the end we save some scripts, some R objects, some data frames with the data already preprocessed, and this way we can move on to the next script. I recommend doing that rather than doing all the process in the same script. Just whenever you make some transformations in a dataset, save this dataset as an RDS object. These objects are how you store something that is without having to, for example, transform it into a CSV file, for example, which you can incur into encoding mistakes or something like that. So then the next script, it's script number 2. It's applying some dimensionality reduction through PCA, principal component analysis, and in R it's quite simple to do that. Okay, what I will do is to delete all the environment, and we will start from scratch. with the already preprocessed files here. Okay. So one of the things that I do here is that I am using this function called near0var. This function comes from the caret package, and it is a very useful function for just removing columns that have very low variance. And in a data set like ours, where you have a lot of undetected signal, you have sometimes the case where a phone is not detecting any router whatsoever, or sometimes it will detect one router, but then that is creating a very sparse data frame. And when you want to run models such as random forest, you don't want these very sparse data frames. They don't deal with them very well. So we just remove the columns that have less than one unique, one different observation per every 3,500. And then, okay. We have to load the caret library, of course. And then if you want to do PCA, sometimes you do it just to understand the data set, right? But in machine learning modeling, it's very useful to run PCA and keep just the components, which are your new features. Instead of modeling with your original features, you will model with components, which are just linear transformation of your previous features, and that means that you will lose some interpretability. For example, some models allow you to check which features are more important for your model, right? And you don't want to have principal components as the features that are more or less important. Your model will not be telling you anything relevant. But if you are just aiming to do a model that it runs faster because you have less features, and it has all the information more condensed, it's very useful. We can do it with or without scaling. We can try in which one of the two PCAs we can explain the most variance in the dataset with the least amount of components. And it turns out that in the non-scaled PCA with only 100 components, we are explaining 95% of the variance of the dataset. So we have now, after all these transformations, we have now gone from 520 WAPs to only 100, and that is what will enable us to iterate through different models and different sets of parameters relatively quickly in our local machine. We can try to explore the PCA to see what it created. This very small plot is that it's impossible to see from here. Let's see if we can created. This basically tells you the percentage of variation that explains each one of your components. So we would have the first component explaining around 14% of the variation of the dataset. And as you see, like if you just got here, all the other components are not explaining anything relevant in the dataset. This is why we could at around 100. You can look it better with this other set of charts. This is like the cumulative chart, the same that we were looking at before, but cumulatively. So we see that at 100 components, we are already explaining more than 90% of the variance. Exactly. Okay, so we have decided to keep only the first 100 components, and that is what we are doing here. We are accessing to the PCA object that we created, and keeping only those, and assigning that to a new object. And then
using 100 variables to explain 900 points of data.
900.
That was your training.
We're using 100 components to explain 95% of what previously were explaining around 400 variables.
The original data set, your training data set is around 900 points, wasn't it? Like it was on 903 and 1000.
Yeah, but those were unique spots where things were recorded.
Yeah, that's what we did. Anyway.
No, what do you mean?
I think there's lots of explanatory variables for so many databases.
So you...
I would use maybe 20, the top 20.
Okay.
I think you would be overfitting.
Okay, we could try that. Look, I will go with 20 only and see how.
Sorry.
No, because I already did it with 100. Let's do it with 20, and we will see. We will be able to iterate faster through modeling, and we will see if those models are accurate or not. It's a good suggestion. If your instinct tells you that, we have to try it, especially since it's going to be faster than going the other way. Okay, it's important to notice that when we do the PCA in the train, we are creating an object that would be like a model, and then we apply this same PCA that we created with the training set to the validation set. We are not doing a new PCA with the validation set. That's to create the same components, so to speak. This PCA object allows you to use the predict function on it with the new data that it's the validation, and then keep only the components that you want. Yep, 20 here and 20 there. No. Okay, so let's make sure that we run everything again. We are now adding the relevant columns, so the columns that we want to predict, our targets, floor, longitude, and latitude, to the PCA, to the components that we kept. And we save both the PCA, that we have to save it to apply to the testing set later, the one that we're going to send to the researchers, and we save also the new data frames that we are going to use to run the models. let me check that we have, 23 variables on each one of the data sets. This means they're ready. Okay. So now we can go again to cleaning our environment and reading the data that we created in the previous script. The data frames with almost all the observations, but only 23 variables. We can check that they have floor, longitude, latitude, and then the 20 principal components. Okay. Before I was using a very small sample of the data to train the models because I had 100 features, but now we can increase a little bit the size of the sample. And to create this sample, I use the caret function create data partition. Like, there are a million ways to do the data splitting in R, but I like that in caret they give you this create data partition function where you can select a variable, typically the target variable, and it will stratify the sample based on that variable that you targeted, and then you just say the fraction of the data that you want to keep. If you get this invalid graphics state ever, it's because you have the developer mode turned on and you want to turn it off, I think. Okay. Here is where, in using caret, you define your cross-validation. You have to create an object called fit control, and in this object you use the train control function, where you say that you indeed want to use cross-validation, which is this process that we described, right? That we divide the training set into a few folds, a few chunks, and then we will be training each model using only a few of these folds and assessing this model with the fold that gets left out. This is basically what enables us to test different sets of parameters in the training phase and evaluate them, and then at the end of the training phase, keep only the best set of parameters, the model with the best set of parameters. So we say this would be the number of folds, the number of chunks in which you divide your data set. And then you can repeat the process a few times, but we're not going to do that. And if you also are loading the package called for each, I don't have it here, I should have it. Here we should have library caret and library for each. For each is what enables that if you have a computer with multiple cores, if it has to grow hundreds of trees, it will use the cores in parallel to grow them, and you can go a bit faster. So we run this function, and then here is where we will use a for loop to train, in this case, 4 models and compare them in just one run, so we don't have to worry too much. We will then store the performance of the models in one object. This is the function that runs the models. It's a train function, and you enter the formula like in every model in R. You select the data. In this case, I'm selecting from the data, because we have more than one target variable. We have to make sure that we are only selecting for each model the target variable that we want, and then the rest of the variables. And then the method is the algorithm that we're running. In this case, it's the I in our for loop. Then you define the metric that you want to use to choose the best set of parameters. In this case, I'm choosing accuracy. And you have the option to do some preprocessing in the training phase. Like you could do some standardization or something here in between. In this preprocessing function, you could also do the PCA inside. Just write PCA here, and it will do it. But I chose to do it separately, so we kind of understand better what's going on there. Then in this same loop, I am saving each model, because then if I want to use it, I don't have to run it again. And I am making predictions on the validation set, and those predictions are the ones that I am using to check the performance of my model later. The predict is the function that I use for making predictions, like always in R. But then you have the posture sample function, which is very convenient because it applies to your ground truth and your predictions the most common performance metrics for either classification or regression. So we can run this loop. And it will take a while. Those are the metrics that I got. So let's see with less components.
Is this on the test or the...
Here we are using a fraction of the training set. For training, we chose 1/10, but then for testing the models, we are using the validation set, which is one set taken 4 months after, and that ensures that our model is not going to overfit, and that it's kind of realistic, the performance that we're getting. If you want to enter in the competition, I would recommend training the model with both validation and training merged together. But if what you want to get are realistic metrics that you can trust, that if you train a model now, they are going to be sustainable in the future, even if some routers change, you should test in a set that was recorded differently and afterwards, and with some differences. And this is what we're doing here. Maybe I overestimated how quickly it would run by increasing my sample here. But to anticipate a little bit what's gonna come later, you get this summary of, in this case, accuracy and kappa of all your models, and then you see which one is the best. In this case, it was, I think, the random forest, the ranger. And once you have it, you can choose to, for example, increase even more the sample that you're using to make sure that you're using as much data as possible, and then train only this particular model that you saw that scored the best results, and tuning the parameters a little bit better. All the models are stored in my computer because I set that in the loop, and by reading these models that you have stored, you can see the parameters that got chosen automatically by Caret. Caret does an automatic search, but of course it doesn't check all the possible parameters. It does. I think it's something similar to gradient descent. No, it tests one set of parameters, and if it sees that the accuracy is super low, it makes a big jump. Otherwise, if the accuracy is getting better, it does a smaller jump, and it does that by a few parameters. In this case, in this ranger algorithm, even though it's a random forest, we cannot set here the number of trees, but we can set mtry, which is for each one of the trees that the random forest is building, how many features are you picking, how many features are going to be candidates to be part of each one of these trees. Split rule, this typically would be like Gini or entropy or one of these criteria, but they came up with these extra random trees, and it means that the split for numerical features in a decision tree gets done very randomly, and that ensures even more that the random forest is indeed random. And then here, with minimum node size, you kind of define how deep you are allowing your trees to grow. Because if it's 5, for example, whenever a node has only 5 or less observations inside, it cannot grow further. So those are some parameters that, in this case, this ranger has, and you can create a grid with a combination of these parameters. Then you can define here the number of trees. You could go higher than that. And you kind of create a model that you saw that was the winner of your for loop. You can tune it a bit better. Let's see. Look, it's growing trees. It's doing it because of the gradient boosted trees. It means that we are in the second iteration. The random forest was built, now the GBM, and those two are much more faster. Yeah, okay. See, turns out those 80 components were useful, and we dropped 7 points in accuracy. That I like the experiment.
Well, it depends. I think it depends how you all then testing on validation.
Well, we're testing. This is on validation, eh?
Yeah. Oh yeah.
And we took a bigger sample. Maybe the balance is between you and me. We don't know. No, but I like that in this problem, by changing some small things, and you can change a lot of things of the processing, and then you can of course try many different models and tune them. You really can. There's room for improvement. In our students, we see that the ones that especially that get to know very well the data set, they usually perform much better. So now you would, after tuning your model, you would do a loop for both accuracy and for both longitude and latitude. Here you would write all the methods that you want. Again, ranger and GVM, etc. And you can go to the Caret website. It has a very good website with a very good explanation of all the lots of features that it has to tune it. And then here you have a list of all the available models. You see that there are more than 200, and if you go and search the model that you are thinking about using, you see the tuning parameters that you have, and then you can create all these grids that we were creating to tune those parameters. So I'm not going to run the models for latitude and longitude because I think we are kind of running out of time. But I have them stored, and what I would do now is to preprocess the test set, which is the one that we will submit for the challenge, the same way that we preprocessed our training and validation set. So in this case, the only thing that I have to change is the number of components, right? And then we would just load from our computer the data, the models that we created and we stored, and we would just make the predictions for floor, for longitude, and for latitude. And then this is the only thing that we have to submit: floor, longitude, and latitude. We write a CSV with these predictions, and we can participate in the competition. So that's all from my side when it comes to talking. But if you have some questions, or especially if you want to go back home and try to do this challenge using my code as reference, but tuning the models in your own way and doing other things in the preprocessing, and if you want to then get your model tested by this researcher in the University of Jaume I in Spain, let me know. I'll show my contact. Where is it? Here. And either if it's for asking some questions or on particularities of the Caret package, or if it's, I was planning to compare the Caret package with some other meta packages for machine learning. Some of the most popular ones are MLR, machine learning in R, and there's this one called H2O that is particularly well suited for scalable machine learning. So it's very performance focused, a bit less easy to use focused. And then the guy who created the package, Max Kuhn, is now working with the Tidyverse guys in our studio to create something that they will call tidy models. And it will be kind of integrated with the whole Tidyverse and using a similar syntax than Caret, with this flexibility for you to iterate through many models very easily. That's all. Thank you for your attention.